Welcome back to SE350 lab. In this lab, we're going to talk about P1. P1 has two parts. The first part, or part A, is fixed size memory pool management. And the second part is the process management. But before I can talk about the fixed size memory pool management, I need to introduce you the board, how to program it. And the most important part is how to create a system call. Now we're ready to write our first operating system. As you know, operating system manages the hardware. So we first need to understand what the hardware is about. And chapter 10 talks about the hardware environment. I would like you to pay special attention to the processor and then the exception handling mechanism. Once we know these two parts, then we can move on to study the software interrupt handling, which is SVC programming. SVC stands for supervisor call. It is a mechanism for the Cortex-M3 processor to create system calls, which is what we're going to do for lab 1. Lab 1, we're going to create 5 system calls. Let's first take a look at the board. The board you've already seen in lab 0. It is a microcontroller unit. The microcontroller right here is made by NXP and it is LPC7068 microcontroller unit. Well, this microcontroller, the inside it, the processor itself is made by ARM and it is Cortex-M3 processor. The CPU can run up to 100 megahertz and there's one system tick timer within the Cortex-M3 processor, which we don't really use. However, there are 4 timers on the microcontroller unit, which we will make use at least one of them. And there are 4 UARTs, which we make use of 2 of them. And there are many other cool stuff like all these things like potentiometer, LEDs, buttons, this stuff like a CAN bus, right? They are onboard peripherals. The onboard peripherals we use actually are these 2 COM ports or RS-232 connectors. These connectors will connect to the microcontroller to 2 UARTs inside this chip. On Learn, I have posted the manufacturer manuals. These are references. The first one is the schematics. The schematics basically is the circuit of the board. So let's say you're interested in how the RS-232 is connected to the on-chip peripheral of UART, then you study the schematics. And for the second one, that is the most important one, which is the microcontroller unit user's manual. For example, if I want to program the timer, I want to program the UART, and I need to set, let's say UART, I need to set the baud rate, and for the timer, I need to set the timer tick value, all these things, right? The counters. Then I need to refer to the user's manual because it lists all the control registers and the data registers and the status registers so that I can program them with. Fortunately, we provide you the starter code on how to program all these on-chip peripherals. So you only need the manual if you really want to understand certain details about the starter code. And the other thing is the data sheets. This is basically a document that contains all the electronic characteristics of the microcontroller. Now let's look at the block diagram of the microcontroller, and I've circled in red the relevant part for our lab project. The most important one is this microcontroller's processor, which is Cortex-M3 by ARM. And then for the on-chip memory, we have 512 kilobytes of flash memory, and we also have 64 kilobytes of static RAM. For the on-chip peripherals, they are basically connected to the ARM high-performance bus. We're going to use the UART 0 and UART 1. We're also going to use timer 0. And sometimes you may want to use timer 1. And there are timer 2 and timer 3 available. And our testing code may use one of these timers. Now let's take a look at the memory map. see we have RAM, we have on-chip peripherals. They are all mapped into different memory addresses. So to access them, you basically just access the memory addresses. For the flash memory, it is starting from the lowest address 0, and we have half meg of flash memory. And we have two banks, I would say two regions of 32 kilobytes of SRAM. And the first one, that's the one we use in the lab. And the second one actually is two banks of static RAM, which we don't require you to program. But if you are interested in to expand your RTOS project so that it can manage this piece of memory as well, you're welcome to do so. It's just not required. And for the most of the on-chip peripherals, they are basically mapped into this memory region. For example, the UARTs, the timers, they are mapped into this memory region. However, for the Cortex-M3, the processor itself, it has its own private peripherals. For example, the system tick timer, the nested vector interrupt controller, they are mapped into this memory region. We will start with the brain of the microcontroller, which is the Cortex-M3 processor. Here's a block diagram of our Cortex-M3 ARM processor. It is a 32-bit microprocessor with 32-bit data path, 32-bit register bank, and 32-bit memory interface. So everything is 32-bit. And then it has this what we call Harvard architecture. It has separate data bus and separate instruction buses. But the instruction and the data buses, they share the same memory space. So it is a unified memory system. Register bank is the most important part of a processor. We have 16 registers in the register bank. R0 to R7 are what we call low registers, and R8 to R12 are high registers. ARM has these ARM's 32-bit ARM instruction set, or 32-bit thumb2 instruction set, or 16-bit thumb instructions. And for our processor, we will thumb instruction sets or thumb2 instruction sets, so we don't use ARM instructions, we use thumb or thumb2 instructions. And for the thumb instruction, it's smaller, so 16-bit wide, and for the thumb2, it is 32-bit wide. And so for low registers, you can either use thumb instruction or thumb2 instructions. And for the high registers, only thumb2 instructions can be used. And there's special registers, the stack pointer. We have two stack pointers, the main stack pointer, MSP, or the process stack pointer, the PSP. However, they are banked, so at any moment, you can only see one of them, so they're shadowed. And the control register decides which stack you will see. And for the R14, that's the link register. That's for subroutine call to hold the return address. And for the PC, is the program counter. So there are a set of special registers. This is what we call XPSR, or the program status registers. It contains three registers: the application PSR, the execution PSR, and the interrupted PSR. But they got mapped into one single 32-bit word so that we can access all these three registers by just accessing different fields, different bits in this 32-bit word. That's the program status register, very important, and contains the information, context information of the processor. And there are also interrupt exception mask registers. We don't have to worry about them for now, but in later labs, when we start to deal with timer interrupts and the UART interrupts, then we will talk more about it. And the main thing is how to mask interrupt and how to unmask interrupt, and also how to set priorities of interrupt sources. And there's finally, there's this control register. It has only 2 bits. It's 32-bit wide, but only 2 bits are used. The bit 0 determines the privilege level of the execution. We're going to talk about the privilege level and operation mode later. And then we're going to have this special the stack selection register, which determines whether you're using the MSP or the PSP. There's a small fraction of the code that needs to be written in assembly, and we wrote most of the assembly code in the starter code, but you need to at least know how to read the assembly code of ARM instructions. So here's the general format of the assembly code of ARM Thumb2 ISA. You can have a label, and then you do your opcode here, followed by the operands. The comment starts with semicolon. You will find frequently used assembly instructions relevant to our lab in the lab manual. I want to point out for general purpose registers, you use load and store instructions, but for special purpose registers, for example, the control register, then you need to use MRS and MSR to move data around. And push and pop for stack register, and here are 3 flavors of branch instructions. These are pretty much all we need for this particular lab. Recall we talked about the Cortex microcontroller software interface standard in our Lab 0. Well, this software stack, actually this abstraction layer provides many functionalities. So now I'm going to talk about these intrinsic functions. It's standardized intrinsic functions. So instead of using assembly code, you can use the corresponding C code to do what the assembly code is doing. And that's probably better for most of us. Here is a list of CMSIS functions. For example, if I want to disable or enable or disable interrupts, I can use assembly instructions. But in the meantime, the corresponding C functions listed here, they do the same thing. Similarly, for control register, read and write, here are the assembly instructions, and here are the 2 C functions. And for the MSP and PSP, the main stack and the process stack, we have similar intrinsic functions. There are 2 operation modes, thread mode and handler mode. And there are 2 access levels, unprivileged or user level and privileged level. The handler mode is for exception handling, and the thread mode is mainly for application. When we are in the handler mode, usually it is some exception happens, so we're doing interrupt handling. And this mode is automatically privileged, so there's nothing called unprivileged handler mode. It is always privileged handler mode. Application usually runs at thread mode. When we're in thread mode, we can either have privileged access or unprivileged access. Upon reset, the default status is thread mode and privileged access. So default is you can run an application. For example, our Hello World application actually was running at thread mode with privileged access. Privileged access basically means you have the full access to the instruction set. For example, you can reset your CPU. Okay, so usually for regular applications, we don't need that full privilege access, and you don't want it to have it either. You don't want any arbitrary application can have the ability to reset your CPU, for example. So we program the control bit and then turn it into an unprivileged access level. And when exception happens, it will bring us to the handler mode. And inside the handler mode, if for some reason we don't want to return back to the unprivileged level access, we want to return to a privileged access level, then we can always program the control bit. Because we're at privileged level, we can program the control register, and then we're back to privileged level access. And usually, the use case of these 2 different modes with, the same mode with 2 different access level is for I/O devices, not just I/O device, but any like device drivers, right? Usually they need some privileged access to a certain memory region. Then we give them privileged access level. And for unprivileged processes, for example, regular user tasks, then we will just give them unprivileged level. The control register decides the operation modes and the stack usage while we're inside the thread mode. While we're in handler mode, there's nothing to set. The processor will bring us to use the main SP and then at privileged level. In thread mode, Depending on the setting of the control register, bit 0 is to set privileged level. So if it is 0, it is privileged. And if it is 1, it is unprivileged. And bit 1 determines which stack to use. If it is 0, then we're using MSP. And if it is 1, then we're using PSP. And the corresponding assembly instruction to set the control register is the MSR and MRS. So this is write, this is read. And here are the corresponding CMSIS functions to do the similar thing. As we mentioned, our lab project is to develop a kernel, and the kernel runs under the exception handler mode. So we need to understand how exception works on this processor. This processor has a nested vector interrupt controller. It has system exceptions and external exceptions. System exceptions, we're mainly interested in the supervisor call exception. Supervisor call exception is a software interrupt. Why? Because SVC itself is an assembly instruction. So I can issue an assembly instruction called SVC followed by a number, say 0 or 1. And this will trigger a software interrupt or exception and brings the processor to exception handler mode. And this is the main mechanism for us to create system calls, which we will talk about later more in details. And these external interrupts are usually triggered by the hardware, for example, the timer or the UARTs, which we will deal with in later labs like P2 and P3. The vector table starts from 0 upon reset, and there are 32 programmable priorities for the interrupts. And every vector table, like each vector table entry, contains the exception handler's address. So this allows the processor to jump to the exception handler when certain exception happens. Exception happens under two different situations. The first one is a simple one. We're in thread mode and exception happens, we enter the exception handling. And the second one is a bit more complicated. It's what we call nested interrupt handling. Basically, we're already in the exception handling process, and then a new exception with higher priority happens. Then the current exception handler will get interrupted by this new exception, and then we enter another exception handling process. When we enter the exception, the hardware will automatically create a exception stack frame. What does that mean? It basically means it automatically pushes these 8 registers to the current active stack. And these 8 registers are program status register, PC, LR, the link register, R12, the intro procedure call script register, and R0 to R3. These 4 registers usually are for the C function input arguments. And then the current active stack pointer is updated because we pushed these 8 registers. Then if we are using PSP, then the SP is switched to MSP. However, in this lab, we never use PSP, so we're always using MSP, so this step doesn't happen. Then the processor will fetch exception handler entry address from the vector table. Remember the vector table, each entry contains the exception handler's entry address. Then finally, the LR gets updated with a magic code called exec return value. Because we already saved the LR on the exception stack frames, now we can basically update this LR. This exec return value contains some magic information. The first information is which stack pointer corresponds to the exception stack frame. And the second piece of information is the operation mode of the processor before it enters the exception handler. So whether it was in thread mode, like this one, or whether it was in handler mode, or this one. This diagram shows what happens to the stack pointer before and after the exception entry. So before exception, here's where our stack pointer is, and this stack pointer in our case will be MSP. And then upon entry, the exception stack frame gets created by the hardware. So these 8 registers gets automatically pushed by the hardware, and the stack pointer has been adjusted by 8 words because there are 8 registers here. And this is the high address and this is the low address. So our stack grows from the high address to the low address. To return from the exception, this particular processor used the mechanism of loading the program counter with a special value called exact return value. So one of these is a valid one, and the one that we're particularly interested in is this one. We want to return to thread mode using MSP. And then the hardware will automatically unstack the exception stack frame. The exception stack frame contains the 8 registers that gets automatically pushed through the stack upon entering the exception handler. We just talked about it in the previous slide. Then finally, it is the interrupt control register update, like clear the active bits and set the pending bits if there is still external interrupt exerted. Now let's take a look at the mode switch and the stack usage of the starter code. Here, I want to remind you the control register. There are 2 bits. Bit 0 controls the access level and bit 1 controls which stack we want to use. By default, upon reset, we're using MSP and we are in thread mode and we're at privilege level. In the starter code, you will see a macro called SE350_demo defined. If this macro is defined, and then we're going to switch to the unprivileged level because we set the bit 0 of control bit to unprivileged. To 1, then that's unprivileged. Everything else stays the same. We don't really change the stack. And then if exception happens, then we're inside the exception handler. And here, automatically, we're using MSP and we're at privilege level. Once the exception handling is done, then we return back to our thread mode and unprivileged level. The exact return value tells we should use MSP and unprivileged and thread mode. And with the control register, we don't do anything about the control register inside the exception handler. So it was set to 1 before, then when it returns, it still uses the 1. Nobody touches it, so it keeps its original value. So that's why we're back to the unprivileged level thread mode using MSP. If we do not have this macro defined, then what happens is we start from this default state, which is MSP thread mode privileged level. And then if exception happens, for example, SVC call, right, a system call happens, then we trap into the kernel and we're using the MSP and we're in handler mode privileged access level. Then once we're done, we're back to its original state, which is thread mode at privileged level. Because again, the control bit 0, nobody touches it. We don't have any software like a code to change the value, so it keeps its original value of 0, which means it is privileged level. And the exact return value, we use the same thing. We indicate we want to use MSP, we want to return to the thread mode. Okay, so this is the starter code. In future labs, you're going to write some processes so that it will run at privileged level. You're also going to write some processes, so they're going to run at unprivileged level. And you're going to do some context switching so that when an unprivileged process gets interrupted and somehow, like you're going to return to a privileged level process, then what should you do? Then you should add code in your exception handler to adjust the control bit accordingly. But that's for later, that especially starting from P2, and I'm going to remind you again in P2. Finally, let me talk about the reset sequence. Basically, what happens when you press the reset button on the hardware or the reset button on the simulator. So upon reset, the hardware will automatically fetch the initial SP value from address 0. So if you look at the starter code, right, you can see we can dereference the null pointer. This sounds like a very unconventional. Imagine you do this on a general purpose operating system like Linux, you're going to get a core dump, right? But we are playing with physical address. So inside this physical address 0, there is the initial SP value. So if you're interested in the initial SP value, you can dereference this one and then get the value. And then what the hardware does, once it has the stack pointer, it will automatically fetch the reset vector entry point. And then the reset vector starts, and the reset vector eventually will run the main program. We just finished talking about exception handling, and you may wonder why are we studying this? Simply because we need to introduce you the SVC and system calls. The SVC stands for supervisor call. It is a software interrupt and it will trigger an exception. And system calls, they rely on the SVC mechanism to trap into the kernel. To write a system call, we use SVC as a gateway. The basic idea is we're going to have separate spaces for user program and the operating system. The operating system is in handler mode, and the user programs is in thread mode. When the user program wants to get some service from the operating system, it needs to do a mode switch from the thread mode to handler mode through a system call. So that basically means a system call needs to trigger some sort of exception. And here we use SVC, which triggers an software exception or software interrupt. So we program a system call. This system call can be directly invoked by the user program, and then the compiler will generate this SVC0 instruction somehow. And then this SVC0 triggers a software interrupt. Then we're trapped into the handler mode or the kernel mode. And inside the kernel, with the provided kernel information about what kind of service do we want, and we invoke the corresponding system call kernel function. So when you read the manual, we give you the description from the user level, but the actual work is done at the kernel level by a corresponding kernel level function called k underscore something. So for example, if I call RTX init from the user program, then this function will trigger an SVC0 exception, and then eventually it will bring the code to the corresponding kernel function called k underscore RTX underscore init. How exactly this user program gets trapped into the kernel and mapped to the correct corresponding kernel function, we will discuss it in later slides. But this is the high-level idea. We call a user function, through SVC0, we trap into the kernel, and the operating system will map this user function to the correct kernel function. And for our job is mainly to write these kernel functions. Now let's take a closer look at what does RTX underscore init function does. This is our OS initialization system call. What happens is upon reset, we're at privileged thread mode. Then we invoke this function by raising an SVC exception. Then we are trapped into the kernel, and it will go directly to the k underscore RTX underscore init function. So whenever the user calls this function inside the kernel, the corresponding function is the k underscore RTX underscore init function. And what this function does is to initialize the memory, the processes. So for example, in project 1, we're going to do memory management. So we need to initialize our data structure to manage this memory. And we need to do process management. So we need to set up data structure for each process. And we need to set up stack for each process. We also need to set up the correct access level and the stack usage, like basically are you using main stack or the process stack inside the initialization. For our project, we use the MSP and processes could be either at privilege level or unprivileged level. The starter code shows you 2 privileged level processes, but most of the processes you're going to create, they're at unprivileged levels. So you need to set the control bit 0 properly during the initialization to make sure when you're out of the kernel, you're back to the correct level of privilege. So now how are we going to program the SVC handler? Well, the SVC handler is an exception handler. So we use the CMC standardized exception name, which is SVC_handler. And it has a return type of void, and it takes no input argument. Writing low-level kernel code involves assembly programming as well as C programming, and we actually sometimes need to refer C symbol from assembly code, and sometimes we need to access the assembly instructions from C code. In order to do this, we need to understand how the compiler generates assembly instructions. The ARM-CC compiler follows this ARM architecture procedure call standard. We are dealing with a very simple situation, so our assumption is function call input parameters and return data types are not floating point or a data type that is bigger than 32-bit. Under this assumption, R0 to R3 are what we call caller saved registers. So if a function call makes a subroutine call, the subroutine doesn't have to save R0 to R3. It is the caller's responsibility to save that. And for the input parameter of a function, of a C function, the first input parameter goes to R0, second goes to R1, and so on, up to 4 input parameters. And in this lab, all our functions has less or equal to 4 number of input parameters. R0 is used for return value of a function. R4 to R11 are what we call callee saved registers. Say I invoke a subroutine call, and then that subroutine call needs to save the registers in this list if the subroutine call make use of any one of the registers inside this list. So that also implies the C compiler needs to generate push and pop assembly instructions to automatically save and restore any registers in this list if that subroutine call make use of some of the registers. R12 is what we call intra-procedure call scratch register. The standard says you don't have to save it, it's not required, but most of the time people may save it for stack alignment purpose. And for the SP, it's the stack pointer, and LR, link register, needs to save it by the callee for return. So as a callee, I need to save R4 to R11, I need to save LR, and PC is the program counter. So let's take a look at how to write a exception handler for SVC. So first we take the standardized name, and then here I have the keyword __ACM. It basically means this piece of code is written in assembly. Wow, this is intimidating. Are you telling me that I'm going to write everything in assembly? No, that's not the case. Actually, the majority of the logic is in C. This is only a stub. Okay, so now I'm going to show you the high-level idea. The high-level idea is we are only going to handle SVC exception that's triggered by SVC 0. Okay, so we have some code to extract the SVC number from the stacked PC because SVC instruction, the number is encoded in the instruction itself. And remember the exception stack frame has the PC, the old PC stacked onto it. So then we extract this information from this memory address and then we extract the number. So if you look at the SVC handler code in the starter code, there's a couple of lines. All it is doing is to get, are we doing SVC 0? If it is 0, then we continue. What we do is we do a multiple load and to populate all these registers with these values on the exception stack frame, because first we get the MSP is here, we load it to R0 now, hence the memory address of MSP. Then we do a multiple load to R0, R3 up to R12, R0, R3 to R12. This is ARM specific. If you studied RISC-V in your ECE 222, you probably haven't seen that, but this is basically what it is doing. It is getting all these values and populate them to the corresponding registers. And then we push the R4 to R11 and LR, and then this is the most important instruction, the branch instruction, and branch to R12. And R12 is right here, right? And we basically use this instruction to load the R12. But imagine if I put a function, a kernel function's entry point into R12 before I enter the SVC handler, then this will allow us to directly branch to that particular function's entry point. So if before I invoke the SVC handler, I put the corresponding kernel entry point, like kernel function entry point in R12, then I can write my kernel function in C. And this is the mechanism actually used by ARM RTOS, and that's why we're using it. But this may not be the best way to do it, and it may have security concerns, but this is the one way of doing it. And now after we're done with the C part, then we're back to SVC handler, then we pop off the registers we saved. See how many we push and how many we pop, and then we return. Now the big question is how I'm going to load R12 with the corresponding kernel function entry point. Well, the straightforward way is to write everything in assembly. So here's an example. This is release memory block. It has one input argument and has a return type. So all we need to do basically is write everything in assembly. And then what we're going to do, we're going to load R12 with the C function entry point. So this is the specific syntax of accessing sync symbol from the assembly language. So that's the reason why we use C, because C and assembly, they work together very well. And then we raise the SVC 0. And you may wonder what happens to R0. Well, the compiler will put R0 as with the first input argument. So when we will branch to this function, R0 has the first input argument. And as long as our function matches exactly same input argument, we're fine with R0. And then when we return, we need to we don't have to do anything about R0 because R0 compiler generates codes so that R0 has the return value of the function. So we just directly return and then we get our return value. That wasn't too bad, just a couple of lines of assembly, but still people may not like it. So now let's see how we're going to write the system call purely in C. Fortunately, ARM compiler provides this intrinsic keyword called __svc_indirect, which takes one parameter. You put a number here. Here we put 0, but you can put 1, 2, 3, 4. So whenever you have this intrinsic keyword, ARM compiler will help you automatically generate SVC, whatever number you put here, instruction. So here's the define the macro so that we don't have to type this long word. We can just use this macro. So how I'm going to write it? This is the user function. So this is the system call interface. So now I'm going to do a corresponding kernel function at kernel level, which matches exactly the function prototype of the user level system call. So this is at kernel level. So here I'm going to extern. I basically declare this is externally defined symbol. Then I'm going to create a function macro of the user level system call. So you can see the user level system call is not a real function, it is a function macro. So what does this function macro do? It actually invokes this underscore, this function. You see the name basically having an underscore. Well, this name can be arbitrary name. I just choose the convention to put an underscore to remind myself this is the function that matches this function macro. And if you look at the input arguments of this function, the parameter list, the first input parameter, when I call it, I put the argument of the corresponding kernel function entry point. And then the first input parameter of this API gets pushed to the second parameter. So this basically is how I call this function. And you may be surprised, there is no function body definition of this function. All it has is an external declaration saying this function has this function prototype and it is a SVC indirect call. So you probably haven't seen that before, a function without any function body. Just this particular keyword saying, yeah, it's a SVC indirect call. But so what happens is the compiler sees this function prototype. It automatically generates these 2 lines of assembly code. And these 2 lines of assembly code are all we need. The first line is to load R12 with the first input parameter. So whenever you have this intrinsic keyword, the first input parameter no longer goes to R0, it goes to R12. So R12 has the first input parameter, and the second parameter goes to R0, and the third parameter goes to R1, and so on. So the register list gets shifted 1 by 1 position. So now I got R12 loaded with the corresponding kernel function entry point. I can raise SVC0. And all these two, like both of these instructions, they are generated by the compiler. Nobody writes it. Compiler automatically generates them. So now we have what we need. We can go to our SVC handler, branch to R12, and then the corresponding kernel function gets invoked. And this is the mechanism we use in this lab.